Welcome to the Greek Ship Corrosion channel. My name is Maryam Ehteshamzadeh. I'm a researcher in the field of corrosion and protection of materials. Chapter 2, Section 3, Thermodynamics of electrochemical reactions. In this video, the Gibbs free energy change in the electrochemical reactions, Faraday's constant, Soule potential. The main reference is Fundamentals of Electrochemical Corrosion, ASM International. Many chemical reactions may be divided into two half reactions, each reaction involving loss or gain of electrons by chemical species, which as a result undergo valence changes. For example, Fe plus 2HCl reacts to yield FeCl2 plus H2. This reaction may be divided into two half reactions. 2H plus 2 electrons produces H2. Iron converts to Fe2 plus 2 electrons. Frequently, the half reactions involve metal surfaces at which metal ions either pass into or are deposited from solution, or at which the valence state of another species is changed. Reminder of oxidation number. The oxidation number is basically the count of electrons that atoms in a molecule can share, lose, or gain while forming chemical bonds with other atoms of a different element. A negative number shows that electrons were gained, while a positive number shows that electrons were lost. The oxidation number is also referred to as the oxidation state. Examples: the oxidation number of chlorine in Cl2 molecule is 0. The oxidation state of ferric ions Fe3+, iron 3+ cation is positive 3, and of ferrous ions Fe2+, iron 2+ cation is positive 2, and of phosphorus -3 minus charge anion is negative 3. The GFE change of electrochemical reactions. If the half reactions occur on physically separated electrodes or metals in an aqueous solution or other proper conducting medium, then a difference in electrical potential is generally observed to exist between them. Consider Fe plus 2HCl reacts to yield FeCl2 plus H2, in which the iron, having lost electrons to form ferrous ion, is oxidized and the hydrogen ions are reduced to hydrogen gas. Fe plus 2H plus 2Cl minus reacts to yield Fe2 plus 2Cl minus plus H2. Fe plus 2H plus reacts to yield Fe2 plus H2. Here, chloride anions are not involved in the reaction. Thus, that is the sum of the half reactions, reduction of proton and oxidation of iron, occurring at physically distinct surfaces. Conceptually, the two half reactions may be caused to occur at physically distinct surfaces by placing iron into a solution of ferrous ions and platinum, which is chemically inert, in a solution of hydrogen ions into which hydrogen gas is bubbled. The arrangement is shown in the figure. This is the left-hand electrode, that is anode, and this is the right-hand electrode, that is cathode. And here is a porous barrier. What is a porous barrier? A porous barrier is indicated between the two electrodes, across which electrical conduction can occur, but with minimum mixing of solutions. There is a potential difference at this liquid-liquid junction, but it is generally small compared to other potential differences and will not be considered in the present discussion. As redox reactions take place, positive and negative charges build up in their respective half cells. If one side becomes too positive or too negative, the redox reactions will cease and electricity production will stop. The porous barrier or salt bridge allows ions to move and balance the charges. Difference in electrical potential between the metal electrodes. The electrochemical cell that results will have a difference in electrical potential between the metal electrodes. Upon connection of an electrical motor, electrons will flow from the iron electrode through the motor to the platinum electrode. If the motor is mechanically and electrically perfect, then the electrochemical energy released by the cell reaction results in an equivalent amount of work. Otherwise, part of all of this energy may be dissipated as heat. Maximum amount of work done that can be obtained per unit of reaction. In the overall reaction, the maximum amount of work that can be obtained per unit of reaction, here per mole of iron, is that of the reversible transfer of the electrons through the potential difference between the electrodes. This is also the W'(R) work. W'(R) is non-expansion work, for example, electrical work, in reversible condition. More about the work term is available in the video titled Chapter 2, Section 1, The First Law of Thermodynamics, the slide number 169. R stands for reversible, represented by the change in the Gibbs free energy at constant temperature and pressure. The negative Gibbs free energy change equals W'(R). If unit positive charge with magnitude equal to that of the electron charge is designated as E+ and C charges are transferred per unit of reaction, then the reversible electrical work is given by W'(R) equals C times E+ times E cell, where E cell is defined such as to be positive when W'(R) work is done as a consequence of the spontaneous reaction. C is the number of charges with unit positive charge per unit of reaction. N0 is Avogadro's number. Conventional electrical circuit analysis considers that positive electricity flows as a consequence of the difference in potential. The electric potential, also called the electric field potential, potential drop, electrostatic potential, is defined as the amount of work or energy needed per unit of electric charge to move the charge from a reference point to the specific point in an electric field. Lorenzo, Romano, Amedeo, Carlo, Avogadro, 1776 to 1856, is famous for Avogadro's law, which states that two gases of equal volume at the same temperature and pressure contain an equal number of molecules. In honor of him, the number of molecules in a mole of a substance is called Avogadro's number. Avogadro's work was largely ignored during his lifetime, but became known shortly after his death, and eventually his ideas were shown to be correct. Little is known about Avogadro's private life, but his obituary 9 days after his death said that he was religious without intolerance, learn without pedantry. Faraday's constant. Faraday's constant is multiplication of Avogadro's number and unit positive charge. N sub 0 or N0 times E+ equals F. 6.02214076 times 10 to the power of 23 times 1.6021766634 times 10 to the negative power of 19 equals 96,485. That is almost equal to 96,500. N sub 0 or N0 is Avogadro's number or constant. E+ is the unit positive charge with magnitude equal to that of the electron charge. Avogadro's constant, commonly denoted Na and sometimes denoted N0. The SI unit of F or Faraday's constant is coulombs per mole, coulombs in joule per volt. Gibbs free energy and Soul potential. Substitution of equation W'(R) equals N times F times E sol into equation the negative Gibbs free energy change equals W'(R) gives Gibbs free energy change of the reaction equals the negative N times F times E cell. Since E cell is defined to be positive for a spontaneous reaction, this equation correctly expresses a decrease in Gibbs function, which is the thermodynamic criterion for a spontaneous reaction at constant temperature and pressure. It's evident that if Gibbs free energy change of the reaction can be calculated from the standard Gibbs free energy of formation data, the potential of a cell arranged for reversible operation can be determined. Conversely, experimental measurements of E cell permit calculation of Gibbs free energy change of the reaction. Challenge number 13. Thank you for your time. If you like to challenge yourself, please answer this question in the comments below. Where was Avogadro born in?